Everybody. That's our second revision, and we are going to do in this revision session AC network. So we'll just go ahead and start solving numerical example. Example number 1. Let's say that we have a resistance equal to 10 ohm in series with inductor equal to 20 millihenry, powered by current source equal IS. IS is expressed as 2 cosine 500t ampere. To solve any electric circuit in AC or sinusoidal AC source, so we should convert any inductor or capacitor to the equivalent reactance. The reactance of the inductor XL is equal omega L. And omega is given here in the equation because it's 2 cosine omega t, so omega is equal 500. So I'll say 500 times the L, which is 20 millihenry. So it will be equal to 10 ohm. So that's the XL. Now we can go ahead and we change the value of L, replace it by XL, and will be positive J, so it will be J10. So now the problem is much easier. Okay, what's required? It's required to find the voltage across the branch V. Okay, so now we want to find V, and we know the current, so just multiply the current by the impedance. The impedance consists of 10 ohm in series with J10. So we'll say the equivalent Z is equal to 10 plus J10. Okay, and to do that, you can sketch the triangle just to make it easy. The resistance is equal 10, the reactance is equal 10. So this amplitude of Z, you can get it just by saying Z magnitude is equal 10 square plus 10 square square root. We'll find Z equal 14.14 ohm. So that's the value of Z. To find the angle theta, so the angle theta will be 10 minus 1 XL over R, which is equal to 10 minus 1, XL is equal 10, R is equal 10, will be equal 45 degree. So Z, now we can write Z is equal to 14.14 on angle 45 degree. And you can save your time and use your calculator that convert the complex form into polar form. You can get it directly, but I just like to explain here how can you get it if you don't have it. Now we found Z. You have to remember what's required in this example. It's required to find the voltage across the Z. To make it easy, I can represent the old Z here. That's the Z that we got, which is equal to 14.14 on angle 45. 14.14 on angle 45. That's Z. And you have a current source, which is equal to 2 cosine 500t. You can say now the current of the source is equal 2 ampere on angle 0. There's no shift, no phase shift. So that's the current IS. So now the voltage across Z, just multiply I times Z. So the voltage should be equal Z times IS. That will be equal to 14.14 on angle 45 times the current, which is equal to an angle 0. So you will get 28.28 on angle 45 volt. You should express the voltage in time domain. So convert this phasor representation to time domain expression. It will be 28.28 cosine omega t. Omega is equal 500 t, and the phase shift is equal 45 degree, and the unit is volt. And you are done with the example. Okay, great. Now let's move to example number 2. There are two elements in series. When we measured the current and the voltage of this branch, we found out that the current is equal to 10 cosine 500t minus 23.13 ampere. And the voltage across this branch is equal to 50 cosine 500t plus 30 degree volt. So we want to find these two elements in series. Okay. How can you solve something like that? Well, if you want to find the two elements, it means that you want to find its resistance with inductor or resistance with capacitor. That's what you're supposed to find. So simply, you want to find the impedance. Great. So to find the impedance, you have to know the voltage and the current. Do we know the voltage? Yes. We know the current also. We know the current. But we agree that it's simple and easy to use phasor representation. So now I'll say the current as a phasor is equal 10 and the angle minus 23.13 degree ampere. And the voltage, it's equal to 50 and the angle is 30 degree voltage. So I can find the impedance directly by dividing the voltage and the current in this form. The voltage is equal 50 on angle 30, current is equal 10 on angle minus 23.13. Doing that would be 5 on angle 30 minus be 30 plus this angle, you add them together. So it'd be 53.13 degree in O. That would be the Z. It changed the polar form into complex form. Let me just write it here. 5 on angle 53.13 degree in complex form would be equal to 3 plus J4 ohm. So the real part will be the resistance and the imaginary part will be XL. So obviously you have plus J, so that's why I write XL. So the two elements in series are resistant and inductor. The resistance is equal 3 ohm. L, I have to find L. How to find L from XL? I know that XL is equal 4 ohm and XL is equal omega L. What's omega here? Omega is equal 500. So I'll say it's equal 500 because let me remind you, XL is equal omega L. So that's omega and L unknown. So L is equal 4 divided by 500. You'll find it's equal to 8 millihenry. So you can put here 8 millihenry and you are done. You found the two elements. Great. Let's move to the third example. All right. In the third example, very simple problem, but it needs just understanding of the relationship between the current and voltage in different elements. The question say that you have an inductor connected to a voltage source and that's XL and the voltage is equal to 100 on angle 0. When they measured the current in the inductor, they found that the magnitude of the current is equal to 4 ampere. They decided that this ampere is high for their application, then they decided to add a resistance to this inductor. So in the same source, the same voltage source, they kept it the same, but they want the ampere here instead of 4 ampere, they want the ampere to be equal to 2 ampere. So they want to reduce the ampere to the half. So the question is, what is the value of R that it will make this job? That's the question. Well, to solve this problem, first you got to know what information do you need and what is the available information. All right. First, you know that it's the 4 ampere in the first circuit and you know the voltage, so and you have only reactance. So if you divided the voltage magnitude by the current magnitude, you can get the value of XL. Because we know that in general, V is equal Z times I. But in the first circuit here, you will observe you have only one. So your Z is equal XL, right? So that you have XL. So XL is equal V or I. The voltage is equal to 100 and the current is equal 4, so it will be equal to 25 ohm. So XL is equal to 25 ohm, so you can say that this one you have it J25 if you want to include the direction. Now, we want to move to the second part. What's the value of R that would make the current 2 ampere? So we got to think, how we calculate the current in a circuit like that. Well, to find that, you got to find Z. Well, Z, if you just sketch the impedance triangle, R, you don't know R. You know X is equal to 25, so this is your Z. So your Z is equal to R squared plus 25 square root, but you don't know R. But you know the current magnitude. The current magnitude always equal to the voltage magnitude divided by the Z magnitude. The current magnitude here that you want to have 2 ampere. The voltage magnitude, it didn't change, the same 100 voltage. So 100 voltage. So what is Z magnitude? So now we can get Z magnitude. It's equal 100 divided by 2, so it will be equal 50 ohm. So now we can write Z that you are looking for is equal to 50 ohm. Great. Now we know the value of Z, so you can find the value of R, because you know that Z is equal R squared plus 25 square root. From this equation you can find R. You'll say R is equal Z squared minus 25 square root. Z now it's 50 square minus 25 square root, and you solve this, you'll get 43.3 ohm, and that's the value of the R that will make the current is equal to 2 ampere. Okay, I hope you like this problem. Let's move to another example. You have Western bridge look like that, resistance equal 10 ohm, another resistance 20 ohm, inductor J2 ohm, another one J6 ohm, connected to a current source IS, and this point A and this point B, this point X and this point Y. It's given IS is equal to 18 on angle 45 degree ampere. What's required? Find the voltage VAB. You want this voltage here. Okay. Well, to find the voltage VAB, and it's not across any element, it's just between 2 points. So once you have something like that, so you start to think about Kirchhoff voltage law. To apply Kirchhoff voltage law, you got to apply it in any loop. So you got two loop. You get one loop here in the top and another one in the bottom that include AB. Which one you choose, it doesn't matter. For me, I will just choose one in the top. So I will say, if I can get, I will represent the voltage here just is not a source. Just I'm saying that's VEB that I want to find, and I'm just sketching the loop that I want to apply Kirchhoff voltage law. and I have here 10 ohm, and I have here J2 ohm, and I need to find VEB. To find the voltage VEB and apply Kirchhoff voltage law, you should know the voltage across 10 ohm and the voltage across J2 ohm. If you have the voltage in both elements known, so it's easy to apply Kirchhoff voltage law. To find the voltage across 10 ohm, you got to know the current. To find the voltage across J2 ohm, you got to know the current. So now, I start to figure out how I solve the problem. So I know the current here, so I just know, I should know how to find the current here. I call it I1, and in this branch I call it I2. IS is known. To find I1 and I2, it will be piece of cake. Why? Because I'm going to use, the rule of current division. To make it simple, you have this branch, 10 ohm and 20 ohm is like 30 ohm. So I can just make it simple like that. We agree that we can make like a small box. It represents any impedance. So that's 30 ohm. And the other branch, you got J2 ohm, J6 ohm. So when you add them together, you get J8 ohm. So J8 ohm. I'm trying just to make it look simple. And that's IS, and that's I1, I2. So to find I1, I will say I1 is equal, I'm using the rule of current divider. So I1 is equal the total current, IS, time the impedance, the opposite, the branch of I1. So it'll be J, that's not 1, that's J8, divided by the sum, J8 plus 30 ohm. I know IS is given 18 on angle 45. So I'll say 18 on angle 45 times J8 divided by 30 plus J8. And in the calculator, it's easy. You can get it. This value of the current. I got it equal to 18. I'm sorry, not 18. No. I got the value of I1 4.65 on angle 120 degree. I advise you, just to work this problem again and try to solve by yourself using your calculator that you got used to. So to be careful and to get used to it before you go to the exam. So that's I1. I2, it will be similar. It will be equal IS, which is equal to 18 on angle 45 degree times, that's I2. I multiply IS by the opposite resistance for I2, which is 30 ohm, divided by the total, 30 plus J8. The same thing, using the calculator, you get I2, 17.39 angle 30.3 degree ampere. So now I got I1 and I2. So you look at the circuit now, that's I1, that's I2. So if the current flowing in this direction, here positive, negative, positive, negative. So if you apply Kirchhoff voltage law, how you write that? Okay, change the color. It's a Kirchhoff. I take VEB as a reference. So you write VEP, and then you look here at the positive, and then you go in this direction. You find positive connected to negative here. So you add, say plus the voltage across 10 ohm. And then when you move to go to the second element in the same direction, you find the positive connected to the positive be minus the voltage across J2 ohm equals 0. You can give it names, by the way, because I call this one X and this Y. So this is called X. And so the voltage across 10 ohm, it's XA. So let's just write it V AB, and that's called XA, I'm sorry, minus and J2 ohm XB. Excuse me. 0. So what's VEB? So VEB, the required will be equal to VXB minus VXA. Now I will find VXB is the same as 10 ohm. So I multiply 10 ohm by the current I1. I got it here. That's I1. 4.65 angle 120. That's VXB. VXA is the voltage across J2 ohm. It's I2 times J2. So J2 times I2, and I2 is equal to 17.39 on angle 30.3 degree. And you solve this equation, you will find the value of VAB. I did it in my humble calculator, 11.72 angle minus 61 degree volt. Okay, so it's solved. So when you solve any problem, as you see the technique here, just see what you want to get, what information do you need, what information did you have, and how you adapt it to the problem. Let's move to another example. That's an easy one. You have 5 ohm and 2 plus J3 for 60 on angle 0, 30 angle 0. We have another branch here, J5, another branch here, 6 ohm, and the mesh current I1, I2, I3. So we need to find the currents. To do that, using mesh current analysis, as I explained previously, it's easy to use the matrix form. So I will say Z times I is equal V. Z will be a matrix 3 by 3. The first element, the total impedance in mesh 1. You look at this mesh 1, you have only two values, 5 ohm and J5. So you have 5 plus J5. And then Z12, it's the common one. You flip the sign, minus J5. Z13, there is no connection between Z13, you just put 0. So that's matrix 0. Let's go to second row. Second row, the first element, Z21, the element between common between 1 and 2, minus J5. Z22, it's the whole thing in mesh number 2, so you got J5, 2 plus J3, 6. Let's just do it here on the side. You got J5 plus 2 plus J3 plus 6. So you have 2 and 6 is equal 8, J3 and J5 is equal J8. So the value here 8 plus J8. You found now Z22. Z23, it's between 2 and 3, it's 6 ohm. You just put minus 6. Here 310 and 32, it's minus 6. 33, you got 4 ohm here, and you got 6 ohm, so the total is equal 10. So we did the Z matrix times the I, the mesh current, I1, I2, I3, in this order as we did. The V1, you got here the current in the same direction, so be 30, an angle 0, and it's positive. 2 doesn't have any source, so be 0. 3, it's in the opposite, will be minus 60 on angle 0. So that will be equation. Also, if you have a graphic calculator, you put the matrix and you solve for I1, I2, I3. Very simple way. Okay. Let's move to another one. I think the last one. So I'll give you a break. Example. That would be Thevenin. Okay. You got here a circuit, 5 ohm and 3 ohm, J4, voltage source, 10 on angle 0, and it's required to calculate the load. You connect the load here, and this load, I mean general impedance, it's equal to 2.5 minus J 6.25 ohm. Okay, it's required to find the current in the load here using Thevenin. So find the load current using Thevenin. All right. We learn from DC circuit theory how to find the Thevenin equivalent by finding the equivalent resistance and the equivalent voltage. Let's first find the equivalent voltage. Remember, when you find the equivalent voltage or equivalent resistance, you got to remove the load. So always remove the load, and call this two terminal A, B, where you put the load. So I will sketch again the circuit to find the voltage. That's 5 ohm, and you got here like impedance 3 ohm plus G4, so B3 plus G4, and you got the voltage 10 volt on angle 0, and you want to find the voltage across AB. So it's very simple. The voltage across AB, it's like the voltage across this Z, 3 plus G4, using voltage divider theorem. So the voltage VEB will be equal to the voltage source 10 on angle 0 time the impedance where you want to find the voltage across, which is equal to 3 plus J4, divided by the total impedance. So if you add 5 and 3 is equal 8 plus G4. So you can find VEB in this way. The value of the voltage that we found here is equal 5.6 on angle 26.6 voltage. Now we want to find the equivalent impedance. To find the equivalent impedance, you just take this circuit, the same circuit, and make short circuit on the voltage source. If it was current source, you make it open circuit. So you replace it by short circuit, means like a wire like that. You have 5 ohm, you have impedance 3 plus J4, and you look here and see what do you find. We'll call it now Z Thevenin, not R Thevenin, because you got Z. So obviously that this element is parallel with this element. So you write Z Thevenin is equal 5 ohm. It's parallel with 3 plus J4. How we find it? 5 times 3 plus J4 divided by the sum. 5 plus 3 plus J4. And find the equivalent. We'll find it's equal to 2.5 plus J 6.25 ohm. That will be your impedance, the equivalent. Now the circuit can be simply represented as one source, which is Thevenin, and we found the Thevenin equal to this value, 5.6, and the angle is equal to 26.6 voltage. And we found Z Thevenin, that's Z Thevenin, 2.5 plus J 6.25. And now we're going to add the load. The load was given there, 2.5 minus J 6.25. So we want to find the current. So we'll find the total impedance in the circuit here. So the total impedance, Z, you add both. So you have 2.5, that's the Thevenin one, plus J 6.25 plus the Z of the load, 2.5 minus J 6.25. It's equal 5, and this cancelled, so 5 ohm. So the total impedance 5 ohm, so the current will be equal to 5.6 an angle 26.6 divided by 5, and you get the current from this. If I'm using my calculator, it's 5.6 divided by 5 equal to 1.12. So it'll be 1.12 and the same angle 26.6 ampere, and that will be the result. I just want to make some simple observation. If you have the equivalent Thevenin and you want to put load here that it draws the maximum power, for maximum power, if you want to find for maximum power, the impedance of the load should be equal Z Thevenin conjugate. So if you want, in this example, to get maximum power, the corresponding Z load will be the conjugate of Z. That's the Z Thevenin, you know. So it will be like equal 2.5 minus J 6.25. So actually what you have here, it is the impedance that will get maximum power. Because when you make the conjugate, you observe that the imaginary part will be cancelled. When you cancel it, so you minimize the value of the impedance. And as you know before from DC circuit, that to get the maximum power, the resistance of the load should be equal to the resistance of the source. That's it. And thank you for your attention, and good luck. And we have one session left for the power. Okay. See you soon.